we've done simple harmonic motion and we've looked at kind of an example already, but I wanted to do just a standalone example of this. So this is still simple harmonic motion. I have a mass on a spring, and it's going to be stretched by a distance of 20 centimeters. After 0.2 seconds, it's going to pass through equilibrium, and I would like to know the maximum speed that this thing moves. So I will write that out. I'm going to also ask, let's find how fast this thing is going when it's halfway to equilibrium. So I have that this thing's stretched 20 centimeters and it's going to reach equilibrium 0.2 seconds later. So I'm given this much of my graph. I'm starting 20 centimeters from equilibrium. And after 0.2 seconds, I'm reaching my equilibrium position. So if I were to continue this drawing, I would get something like that. This thing is a quarter wave. If I cut this in half, I've got a quarter wave here, a quarter wave here, and then to get back up, I've got a quarter wave. So I have 4 of those, which means if this is 0.2 seconds, then this one is 0.4, 0.6, and this is going to be 0.8 seconds. I'm being careful because this says this is when it passes through equilibrium again. It doesn't say it comes to rest again at that time. If it said comes to rest again, that would be here. That's where it first comes to rest. But when it passes through equilibrium, that's this location, 0.2 seconds. You don't have to draw out a graph, but man, drawing it out sure makes things easier. I want to find the maximum speed, and I remember that my maximum speed was equal to omega times my amplitude. I've got my amplitude right here. That's convenient, so I just need that omega. I also remember omega is equal to the square root of k over m, but that's not helpful to me. So maybe I go a different route. Omega is equal to 2 pi times the frequency. Well, that can be good. The frequency is 1 over the period, and the period is 0.8 seconds. So equals 1 over 0.8 seconds. Now 0.8 is 4/5, so 1 over 4/5 is 5/4. So that's going to be 1.25 hertz. My natural frequency, which is 2 pi times f, is going to be 2 pi times 1 1/4. 2 times 1 1/4 is 2 1/2. 2 1/2 times pi is 7.85 radians per second. So I can plug that in. My Vmax is omega times my amplitude is 7.85 radians per second times my amplitude of 0.2 meters, and 7.85 times 0.2 is 1.57. That is meters per second because I put this one in meters. So there's my maximum speed. I also want to know its speed when it's halfway back to equilibrium. These are both kind of trick questions. They come up a lot. finding a maximum speed, a lot of times people will say 20 centimeters over 0.2 seconds is 0.2 over 0.2, that's 1 meter per second, which wouldn't be the maximum speed, right? That would be the average speed. The maximum speed works out to be 1.57 meters per second because you're moving faster when you're getting through equilibrium than you are. You're not doing this all at one constant speed. Finding the speed when you're just halfway back to equilibrium, the temptation there is to say, well, if it's 1.57 here, it's probably 0.785, which is half of this, 0.785 at the midpoint. But that's not true either. When it's halfway back to equilibrium, we get something like this. We're going to say we initially have all our energy being potential is half K A squared. When we're at that other spot, end, final, which is not really a final, I suppose, we're going to have some potential energy and some kinetic energy. So our potential energy is half K x squared. Our kinetic energy is half mv squared. And what we know is that these have to be equal to each other. So I have an equation right here to work with, right in the middle. I'm going to cross off my halves because I've got them in every term. So I get K times A squared equals K times X squared plus M times V squared. I'm solving for V, so I'm going to move this thing over. K A squared, but you know what? I can factor this out already. I'm going to get a K times an A squared minus an X squared equals an M times a V squared. I'm solving for V, so I'm going to divide by M. K over M, A squared minus X squared equals V squared. And now I'm going to take a square root. V equals, I've got a K over M that goes under a square root, and I've got a square root here, A squared minus X squared. The square root of A squared minus X squared is not A minus X, right? This thing is not equal to A minus X. If you're not sure, make up a value for A and a value for X and see how that doesn't work out. This is exactly the same as Pythagorean theorem. So I've got this. Square root of K over M is conveniently, that's my natural frequency. So I can say this is going to be omega times the square root of A squared minus X squared. And this equation, by the way, right here, is always true. When we are looking at the equilibrium position, x is 0, that goes away, and we get omega times A, which is what we knew it was supposed to be. But this equation is always true. So we can actually stick that one in the tool belt too and be able to use it. I get a natural frequency which was up here 7.85 radians per second. And I'm going to multiply that by square root of the amplitude squared minus this new position, which is halfway to the amplitude, squared. And when I do all that, I get a speed that is 1.36 meters per second. It is a smaller speed than I had through equilibrium, which is good, it has to be, but I've picked up most of my speed already by the time I get to this location. looking at my graph, I know that my speed is represented by the slope of this graph. And so I just want to make sure that this makes some amount of sense. When I'm at this halfway point, my slope is already fairly steep. When I'm passing through equilibrium, so there's my slope here. When I'm passing through equilibrium, yes, my slope is steeper, but over here at the top, my slope is flat. So I will have picked up most of my speed by the time I get to that halfway point. That's it. That's an example going through simple harmonic motion with springs and really trying to hit it in as representative of a way as what you might find.